Good morning. Today I want to finish up chapter 2, and so we can begin chapter 3, diodes and diode circuits on Wednesday. There are a few concepts that we have to go over, and so we'll go over those and then talk a bit about IC fabrication in the last 8 or 9 minutes of today's class. Okay. Your section. Okay. So I believe we had stopped here. We talked about introducing external impurity atoms into our intrinsic semiconductor in a bid to increase the amount of charge carriers. If the atom is from column 5, we call them donor atoms because they have an extra electron in their outermost orbit, which is now free to move about and conduct charge through the lattice material, silicon material. So the process of introducing these atoms or extrinsic semiconductor atoms dopant impurity in intrinsic semiconductor. So the process of introducing, well, the process can be either ion implantation or diffusion, but the amount of atoms we introduce into our intrinsic semiconductors is defined by the word called dosage, exactly like the, like a medication dosage. And it is given or counted as the number of atoms per centimeter cube. Okay. So the number of atoms that are introduced into an intrinsic semiconductor per cubic centimeter of volume. And typically these numbers are about 10⁻13 to 10⁻21. Okay. So if it's a column 5 element, then it has 5 electrons. It donates an electron, and so they are known as donor atoms. Column 3 elements have 3 electrons, so they accept electrons from the silicon atoms, and so they are known as acceptor impurities or acceptor atoms, and they are noted by ND and NA. Okay, all uppercase, all capital letters, ND and NA. Of course, they are also listed as the number of atoms per centimeter cube, okay, per cubic volume. Now, typical silicon atoms, the intrinsic charge carriers in a typical semiconductor or typical silicon atom, about 10⁻⁹, 10⁻10. So compared to those, the external impurity dopants is magnitudes higher. Okay, compare 10⁻9 to 10⁻13 or 10⁻20. Yes. Yeah. Yes. The question, yes, and then? Okay, repeat the last sentence. Okay, so the question being asked is about how is column 5 a donor, right? Okay, so column 5 atoms have 5 electrons in the outermost shell. When we introduce them into a semiconductor, let's say silicon, for example, 4 of the 5 electrons will bond with 1 silicon atom each. And so they have now 8, there are four intrinsic electrons plus 4 from the, let's say it's, column 5 element, whatever that might be. 4 plus 4 gives you 8. So there's one extra electron left over. And so now we are donating that electron for charge conduction. And that's why they're known as donor atoms. Column 3, on the other hand, will have 3 electrons. And so it has an empty spot. And when you place that empty spot in close proximity with other silicon atoms, electrons have the propensity to jump into an empty spot. And so they are accepting electrons from one of the silicon atom. And then when that silicon atom becomes empty, or one electron in that silicon atom becomes empty, a nearby electron can jump into that spot, thus by propagating that empty spot throughout the silicon lattice. And so it's an acceptor element. Okay. So we have intrinsic carriers and we have extrinsic carriers, right? Intrinsic are due to thermal generation. In an N-type material, you'd have electrons and holes due to thermal generation, right? Breaking off covalent bonds. When you introduce, let's say, a column 5 element, we have an excess of electrons that are now available. So the excess of electrons are present regardless of temperature. So in an N-type material, for instance, you have intrinsic electrons, intrinsic holes, plus the extrinsic electrons from the impurity dopant. The intrinsic carriers are present due to temperature, so they are dependent on temperature. But the impurity dopant electrons, they are present regardless of temperature. So this is the big difference between impurity doping versus intrinsic charge carriers. And so extrinsic carriers are temperature independent. And then intrinsic charge carriers, of course, are dependent on temperature. Right? All right, let's take a 10-second pause. Let me know if you have any questions. Any questions? Okay. So if you have a whole lot more electrons or holes, as the case may be, we say that there's an excess of negative charge, hence we call it an N-type wafer. If it's excess of holes, acceptor atoms, then it's excess of positive charge, we call it P-type. But those are the carriers that are available to conduct charge throughout. But the next key point to remember is that the overall charge will still be neutral. If we take intrinsic semiconductors, an electron breaks through the bond, but that electron is balanced out by the positive charge, right? It's charge neutral. When we introduce acceptor or donor atoms, let's say we introduce donor atoms, now we have excess electrons that are free to move around and conduct charge through the material. But each one of those electrons is still balanced out by the proton that is present in the nucleus or the nuclei of those atoms. So overall, the charge is still neutral. And the assumption we make when we want to perform any calculations on this semiconductor material is given by this charge neutrality equation, which states the overall charge will still be neutral. Right? The charge carriers are free to move around, but those charges are balanced by the protons that are present in the nucleus. So the negative charges are balanced by the positive, and in acceptor atoms, the positive charges are balanced by the negative. So in this equation, of course, we have 5 terms. Q is the standard charge, standard unit charge. P and N are the number of electrons and holes, the intrinsic numbers. And then ND and NA are the numbers that we introduce into our silicon structure or a semiconductor structure. Okay. And again, we are simply skimming the surface, right? This chapter, this course is about circuits using semiconductor devices. This is simply the first step in learning how semiconductor devices are created. So there's a whole lot more that goes into these equations. But for us, mostly these equations will be kind of plug and solve, right? Out of 4 or 5 quantities, there will only be one unknown. Everything else will be known to us. We plug it in and we solve for that unknown quantity. In real life, if you're working as an engineer, there are lots of variables that you have to take into account. And so it's an iterative process. We pick a starting point, we make an assumption about one quantity, and then we find the answer for the unknown quantity. If it works for us, then we stick with it. Otherwise, we go back to the beginning, we make a second assumption, and then redo the entire calculation again. Okay, so from here, let's look at equations for ND and NA. So in an N-type material, ND will always be larger than NA. In a P-type, NA will always be larger than ND, right? Now, in a N-type material, it is possible that Na may be 0, and a P-type material, it is possible that Nd may be 0. Regardless, this equation would work for most cases. Okay? Yes. For the most part, yes. Yeah. For the most part, this equation would work. So Nd minus Na, again, if it's N-type material and we don't have any acceptor atoms at all in there, then it's simply Nd. Okay? Simply Nd. All right. Now, when you introduce these atoms, stating the dosage is high compared to the intrinsic carrier. So the number of atoms you're introducing is 10 raised to 13 to 10 raised to 21. And so to use a real life analogy, if you have a room like this, you introduce more and more people in there, there's less space to move around. Okay. So the speed and the space and the areas that the electrons and the holes can move is now restricted because there are now extra atoms in that lattice structure. Okay. And those are concentrated in a very small amount of space. Okay. Concentrated in a very small amount of space. And so what it does is it reduces the mobility. So this is a chart starting from the left, going towards the right. On the x-axis, you have the impurity concentration increasing, starting from 10 raised to 13, going all the way to 10 raised to 21. And right around here, you actually see it being lowered drastically. Okay, it's just because of the number of atoms that are introduced in the lattice structure. The electrons and the holes cannot move around as freely as before. Okay. Okay, 15 minutes. There's plenty of time. All right, any questions thus far? There is one more concept that we look at before we get into IC fabrication. Okay. And that concept is, well, actually, there's two more: diffusion current and thermal voltage. Okay. So when we implant these atoms, the external dopant impurities into a semiconductor, as I said, it's in a very small spot, tiny spot, and we try to control the dosage, meaning the number of atoms that are going in. We also try to make that as uniform as possible. But again, we are all governed by laws of physics. So that doping profile is not usually uniform across a physical dimension. So dopant profile or doping profile is not uniform. Okay, so the concentration of atoms just a few nanometers over could be different, from right next to it. And so because of this, a gradient develops. And because of this gradient, in terms of the number of atoms or atom concentration. And like all physical things, all physical quantities, it moves from higher concentration to lower concentration. So still similar to pressure, similar to temperature. Temperature goes from higher temperature, flows from higher temperature to lower temperature environments. Pressure goes from higher pressure environments to low pressure environments. Similar to that, you have a higher concentration of atoms in one area. It will try to diffuse through the material in a way to actually, make the distribution uniform. And because it flows from a higher to lower level, it gives rise to a phenomenon that is known as the diffusion current. It is moving, or the charge is flowing in a bid to make the charge uniform across that physical dimension. And that current is known as diffusion current. Flows from higher concentration to lower concentration areas. This is defined as diffusion current. So here, of course, is the higher concentration. This, and on the left is lower concentration. And the carriers are moving from higher to lower. So it's the inverse of the slope of the gradient. Okay. And total current in the doped semiconductor like this one would be due to the drift as well as the diffusion. Okay, drift as well as diffusion. And this phenomenon occurs in diodes and transistors. Okay. All right. One final concept is of thermal voltage. Right? You've heard in physics, you may have studied where if you have two dissimilar metals together, it gives rise to a voltage due to temperature effects. Right? It's a similar concept. And we will see this term VT in many of our equations. It's a prominent part of the diode equation. K is the Boltzmann's constant. T is the temperature in Kelvin. And so again, this is just dependent on the temperature. Unit charge. And VT has a value of about 25.8 millivolts at 273 Kelvin. Okay. VT, thermal voltage, is due to the voltage that arises because of temperature differences of holes and electrons. Okay, so it's a factor in how our devices behave at different temperatures. Yes. So it's a thermal voltage that arises due to temperature differences. Well, not temperature differences, but due to temperature. Yes. It's similar to the voltage that arises between two dissimilar metals due to temperature. Unit charge. 1 unit charge. All right, I have about 9 minutes left, and I want to. So I got a few pieces of show and tell. These are actual silicon wafers processed. Don't open those, or you don't want to take those out. These are very silicon wafers are very brittle. Okay, so like a wafer chip, if you like just drop them from like maybe a few inches high, they would just shatter and break into pieces. Okay, those ones are academic wafers, typically 4-inch wafers that I use for my research work. Those are from an industry. A former student from earlier this year was interning at a company in San Luis Obispo called Revasum, Revasum. They made chemical mechanical polishing grinders, CMP. So these are some wafers that are basically not useful anymore. And so they were throwing them out. So I said, give me and I can use them for show and tell. Anyway, so IC fabrication is, again, it's an entire field of study by itself. But as engineers, you should still be familiar with a couple of steps of this process, right? So right here, I have the top view of a simple device. Typically, when we work with silicon wafers or any kind of semiconductor material, we are typically using only the top surface. We are pretty much working in the XY direction. So if this is a side view, let's say here, the 4-inch wafers that you see are only 500 microns thick. 500 microns is about 0.5 millimeters. Okay, 0.5 millimeters. That's basically the thickness of some of those mechanical pencils, right? So if this is 500 microns thick, the devices that are built on here is probably about 0.5 microns to 1 micron. 1 micron is considered very thick. Okay, it's considered very thick. If we try to grow, there's one silicon wafer where I have like oxide grown on it. Silicon oxide is basically glass. So if you hold it up to light, it will show you like nice, shiny, different colors. Plain silicon wafer is just gray, shiny gray. Did you pass them to the back? All the way to the back? Yeah, just pass them all the way to the back. Yeah. And so that oxide thickness is probably counted in like 0.1 or 0.2 microns. Very, very thin. Okay. So we typically, if we make microchips, they are in the top less than 1% compared to the thickness of the entire wafer, right? The rest of it is like wasted, not used at all. And here is a device where you have a N-type silicon wafer from the factory. There's an N-type wafer. When you buy wafers, on top, there is a label on top which tells you the type of the wafer, the size of the wafer, the resistivity, meaning the implanted. And all of those are basically predetermined at the factory. We can pick and choose what we want depending on our application. Okay, so there are websites on the on the internet where I can go, and I've purchased like silicon wafers for use for research work. And we can pick and choose what kind of doping we want, what kind of dosage we want, N-type, P-type, 3-inch wafers, 2-inch wafers, 4-inch wafers, all the way up to 12-inch wafers. There's silicon, silicon carbide, germanium, quartz, glass wafers. There's a whole different variety of wafers that we can buy. So this one here is an N-type silicon wafer, meaning from the factory itself, it has implanted impurities. And that's how we would buy these wafers. There's a background concentration that is available, and we buy it. And then we want to create our own P-type device in there. So this is basically our P-type silicon. So when we work with these wafers to manufacture chips, it's always from the top down, right? We are working in 2 dimensions. You're working in 2 dimensions. So you see those wafers, the point of passing these around is so you can visualize that these are so tiny, we can't like actually go in there with our hands to do anything, right? Everything has to be done with tools, specialized tools and equipment, and has to be done at a large scale. In the sense that if there is a 4-inch wafer and we wish to create this tiny, let's say 100 micron by 100 micron opening, we cannot just work on 100 micron by 100 micron size in that silicon wafer. Whatever we do is going to affect the entire wafer. Okay, so let's begin. This is where we take the cross section of the device. And I'm going to have to wrap this up very soon. This is a side view. Now, if this is a side view of one point of the wafer, I'm going to grow. I want to implant P-type into my wafer, right? So if I want to implant P-type into my wafer, going from the top, it's going to go everywhere. There's no way to control it, right? There's no small dimension small enough to just go in one spot area. It will go everywhere. So the way we do it is we protect the areas where we don't want it to go. And then we just have tiny openings where the dopants can go in. So the process that we use is known as photolithography. It's basically like a photographer's darkroom. We spin photoresist chemical on top of our wafer, or we deposit it, cover it entirely with photoresist. We open it up. And so now when we implant ions, so this is open. When we implant ions, the dopant impurities, only in the areas where it's open is it going to go into the silicon wafer. Everywhere else, it's going to go into the photoresist or the oxide and stops. It does not go everywhere. It only goes into the open area. Everywhere else, it goes into our protective mask. So you're going from the top, and that's why you see those different designs. When you look at, you see those squares, each one of those is a chip. So now here is our P-type silicon is making contact with our N-type silicon right here. And thus we have a P-N junction right there. This is important to remember. Actual devices, you have your one type of material below, and from the top, you're implanting a second one. When we actually look at our device, in chapter 3 and 4, those will simply be a representation of P and N junctions coming together. So you'll kind of like see not even a side view, not even a top view. You'll simply use it as a theoretical concept. But in real life, it's not just 2 junctions coming together separately. It's basically one type of material is already present, and you're implanting a second type of material from the top. And only in certain areas. And that's how we create those PN junctions. Okay. So again, this is my entire graduate education was about microfabrication and MEMS, micro nanofabrication and MEMS. So this is an entire field by itself, not just a single course. If you do wish to take this course, it is EE 424, offered only once a year in the winter class. Ben Hawkins teaches the class, and then we also have the lab class that is associated with where you actually go into the clean room and use those 4-inch wafers to build your own microchips. So having said that, I'm going to end class here today, and then we will pick up, not pick up here again. This is basically just the same thing. Aluminum contacts separated by the oxide material. So now I'm going to end class here today, and I'll pick up with chapter 3 on Wednesday.